Hello everyone. In this lecture, I am going to explain Jacobi method, which is useful to find all the eigenvalues of a symmetric matrix. Before going to that, let us recall some useful definitions. The first definition is eigenvalue and eigenvector of a matrix. Let A be a square matrix of order n. Then a scalar lambda is said to be an eigenvalue of A if and only if there exists a non-zero vector x such that Ax equals to lambda x. If we multiply a given matrix A with some non-zero vector x, then the product Ax should be in the form of lambda times of the same non-zero vector x. Then lambda is said to be an eigenvalue. Then that non-zero vector x is said to be an eigenvector corresponding to the eigenvalue lambda and vice versa. That means if lambda is an eigenvalue of A, when satisfying this condition, then x is said to be the corresponding eigenvector. Similarly, x is said to be an eigenvector of A, then lambda is its corresponding eigenvalue. Some of the useful results that we are going to use them here. The first point is, for a matrix of order n, there will be n eigen values. The procedure we are not going to see here, as we are using numerical methods. The second point is, if A is given, then its inverse is given by A inverse equals to 1 by determinant of A adjoint of A, if that A is not equal to 0. The third point is, if lambda is an eigenvalue of A, then the eigenvalue of A inverse is 1 by lambda, corresponding to an eigenvector x. That means if lambda is an eigenvalue of A, then its reciprocal is the eigenvalue of A inverse. Next point is, if lambda is maximum eigenvalue of A, then 1 by lambda is the minimum eigenvalue of A inverse. In a similar way, if lambda is the maximum eigenvalue of A inverse, then 1 by lambda is the minimum eigenvalue of A. The same can be written in another way. If lambda is the minimum eigenvalue of A, then 1 by lambda is the maximum eigenvalue of A inverse. Next point is, a matrix A is diagonalizable if there exists a matrix P such that D is equals to P inverse AP, where P is a matrix formed by taking the eigenvectors of A as its columns. And the resultant matrix D is said to be the diagonal matrix, whose diagonal elements are the eigenvalues of the matrix A. Next point is, the matrix A is symmetric if and only if A transpose equals to A. If all the elements of A are real, then the matrix is said to be a real symmetric matrix. The eigenvalues of a real symmetric matrix are always real numbers. Next point is, in a matrix A, the off-diagonal elements are the elements other than the diagonal elements. I am giving an example here. I have taken a 3 by 3 matrix. In this, the principal diagonal elements are 1, 2, 6. This is said to be diagonal. The elements are diagonal elements. It is shown with pink color. And all other elements are shown in green color. They are all said to be off-diagonal elements. Let us see Jacobi method in the next lecture by recalling these definitions whenever required. Thank you.